Hello everyone. Today our talk is about the effect of unsteady separation on the wall heat transfer during the interaction of exosymmetric vortex ring with a heated wall. I would like to thank the NSF and the High Committee for Education Development in Iraq to support this project. The objective of our problem is to understand the detailed physics on the upper side of the near wall heat transfer during the vortex wall interaction. There is many application of this problem, especially in jet flow, like cooling of plate gas turbine, cooling of electronic spark, and drying of papers, and so on. So the description of our problems, as you can see it here, it's an exosymmetric vortex ring interact with a constant temperature heated wall, and because of the flow symmetry calculation are conducted in a single azimuthal plane where the computational domain is bounded by three walls and the axis of symmetry. Uh, here I here I notice the core radius of the vortex ring. Gamma naught is the circulation. R naught and Z naught are the initial coordinate uh, of the initial location of the vortex. We initialize the radial and wall normal velocity component using Gaussian vorticity distribution and the vortex core using this equation below. For the temperature field, we use unsteady diffusion solution uh, of the semi-infinite domain to avoid the step change in the temperature near the wall in the early evolution of the thermal boundary layer, and also to have a suitable thickness of the thermal boundary layer. So that case I described is we call it case one, and because this work is presented here, focus on the understanding of the effect of unsteady boundary layer separation on the wall. We adopted a novel approach where an identical case, hypothetical case actually, uh, by setting the boundary layer wall shear stress equal to zero in order to study the effect of separation on the heat transfer wall. So after we did the simulation, as you can see here, we got these two videos, and all what I will show the coordinate is related to the core radius. We can see here the velocity vector and the vortex field, the temperature field right here, and the line plot is the radial distribution of the Nusselt number. You can see here the Nusselt number exhibits a maximum in the downward side of the vortex and the minimum on the upward side for both cases. The black broken line marks the position of the minimum Nusselt number all the time, and if you focus on the minimum, we see that for the case one, it's moving to the center of the core vortex, while here in this case is staying at almost the same radial location. So in order to understand this behavior, we look at the minimum Nusselt number values and comparing them for both cases and comparing them to the unsteady diffusion solution. So we see in both cases they are showing the same overall qualitative trend decaying with time. We also note that for case tau equals 0, the red line except a lower Nusselt number values. So this result is rather surprising as it shows that in the absence of the boundary layer separation, the heat transfer deterioration due to the vortex wall interaction is worse than if the separation occurred. So, a closer look at the temperature field near the wall, as you can see in these snapshots for case 1 top and tau equals 0 on bottom. So for both cases give us some of understanding of this behavior. So the black broken line represent the radial location of minimum Nusselt number, while the white broken line represent the upwelling of the isotherm away from the wall. So if we focus for case tau equals 0 first, we see that early in time the location of minimum Nusselt number is very close to the location of the maximum thickness of thermal boundary layer. Following the ridge from the edge of the thermal boundary layer to the way where it's intersect with the wall, uh, the intersection point is corresponding to the location of the minimum Nusselt number. And as the time progresses, this upwelling remains connected to the upwelling, I'm sorry, it's remain connected to the upwelling of the edge of the boundary layer along the white broken line. And comparing to the case 1, we see that early in time, before the separation, the near wall upwelling remains connected to that thermal boundary layer, as in case tau equals 0, but the location of Nusselt number is moving to where the core center of the primary vortex. And after separation, a significant difference is seen in the thermal boundary layer behavior, where the near wall upwelling becomes disconnecting. This one, it's disconnecting from the thermal boundary layer edge, which driven by the primary vortex. This associated with the further movement, like this one, of the minimum Nusselt number toward the vortex center and even in the downward side sometimes. Such a large movement is not seen in case tau equals 0, and this observation suggests that case tau equals 0, in case tau equals 0, that the boundary layer thickness and the Nusselt number deterioration seem to be driven only by the primary vortex, while in case 1 is caused by more complex near wall behavior, especially after separation, that caused the minimum Nusselt number location move significantly toward the core center. So to get better understanding of what is causing this significant movement, we look at the near wall vorticity as you can see in this slide. So at tau equals 0, sorry, the two flow looks almost similar, except for the presence of the thermal boundary, the boundary layer in case 1. As the boundary layer becomes thicker and separate the Nusselt number location, minimum Nusselt number location is getting displaced toward the core center. And we see the separation, that separation of the shear layer, it is lifting up, and then the formation of the secondary vortex. So the synchronization and movement between the separation point and minimum Nusselt number, supporting the idea of blockage of the separated shear layer, as in this figure. So in this figure we show that the radial location of minimum Nusselt number and the radial location of the separation point. So even before the separation, the movement toward the center seems to be connected to the growth of the boundary layer thickness that associated with the flow blockage. So if you focus on the top video right here, you'll see that at the as the secondary vortex takes off and the shear layers collapse, the minimum Nusselt number return back to the upward side. So to show the connection between the near wall maximum upwash and the minimum Nusselt number, we go to the we plot the radial location of the maximum wall normal velocity at the first node right above the wall and the radial location of the minimum Nusselt number. So the connection between the upwash velocity. So sorry. So as see from this figure, the radial location of maximum wall normal velocity is always found upstream of the location of the radial location of minimum Nusselt number, and in both and in both of this plot we see that there is a strong correlation between in movement back and forth between the two locations. So furthermore, we also plot the wall normal velocity at the radial location of minimum Nusselt number for the four four time steps we explained in the previous slide. So the wall normal velocity profile are shown here for the two cases. So the upwash near wall, the upwash near the wall is larger in case tau equals 0, as you can see here, and this is likely the reason why the minimum Nusselt number is worse for this case. And we also notice that the upwash at the last these two time steps is on the downward side because they are negative. And as seen from this is the positive right near the wall, and this local upwash causing a local thickening of near wall sublayer independent of the global thickening of the thermal boundary layer, which is connecting to the upwash of the primary vortex alone. So in conclusion, uh, the deterioration in heat transfer is larger without separation. The movement of the radial location of minimum Nusselt number due to the motion of the unsteady separation and the blockage of the flow in the separation zone. The upwash velocity is the primary driver of the Nusselt number deterioration. So for case 1, the upwash velocity is produced by blockage in the primary vortex induced velocity by the separated shear layer and the interaction with the secondary vortex. For case tau equals 0, without separation, the upward velocity is produced only by the primary vortex, and minimum Nusselt number remains close to the maximum thermal boundary layer thickness. By that, I will finish my talk, and if you have any question, please let me know. Thank you.